welcome back in today's lecture. I am Dr. Milind Meshram, working as an assistant professor in the Department of Chemistry, Hete Chem College, Nashik. In the previous lecture, we have discussed the 1,2 disconnections, 1,2 disconnection with carbonyl compounds. So these disconnections are 2 group disconnections. Afterwards, we have seen the 2 group disconnections which involves the 1,3 disconnections. So first 2 disconnections, so that is 1,2 disconnections, we have seen here the synthon which is used for the epoxide, that is one synthon. Other synthon that is used for the halo carbonyl compounds. Okay, so we know the reactivity of this epoxide is also that is the more electrophilic in nature. So epoxide is acting as a good electrophile. So other synthon that is related to this alpha halocarbonyl compounds. So in that alpha halocarbonyl compounds, the halogen is adjacent to the carbonyl compounds, so it makes it extremely reactive electrophiles. Okay, so third synthon we have seen, that is alpha beta unsaturated carbonyl compounds, so that involves the 1,3 disconnections. So these 3 disconnections we have seen in the previous lecture. In today's lecture, I will be talking about the carbon-carbon disconnections. Okay, so disconnection we have made so far all have been of CO linkage, that is ether linkage, then CN amide bond, okay, amine bond, then we have seen CS, that is thioether linkage. So we have seen these linkages, these cleavages in the 1 group disconnection as well as 2 group disconnections. So of course this carbon-carbon disconnection is also very important, because the carbon-carbon bond forming reactions are very important in the organic synthesis. The disconnection, whatever we have seen for CX disconnection, so analysis for this particular carbon-carbon bond disconnection is similar to that of the analysis for the CX disconnections. Okay, so let's have an example. Carbon-carbon disconnection. Okay. So this is our target molecule. In this target molecule, the reactive functional group is alkyne. Okay, so and this alkyne, so we can make by substitution reaction. Okay, so this we can make this cleavage, this carbon-carbon cleavage over here. So let's put this retrosynthetic arrow, carbon-carbon disconnection. Okay, so we will get this 2 synthon. So one carbon will have this negative charge and other carbon will have this positive charge. Okay, so let us translate these 2 synthon to their respective chemical equivalent. So as this carbon is having positive, so positive charge, so we can add bromine over here. Okay, so this is plus base. Okay, so this proton is more acidic, so it will, this carbon will have the partial negative charge. Okay, so naturally after cleaving this bond, this carbon will have the negative charge and this carbon will have positive charge. So after cleaving this bond, carbon-carbon disconnections, we would get these two fragments, so which can be translated to its corresponding chemical equivalent. These are the chemical equivalent. Okay, so this is about the retrosynthetic analysis for this particular target molecule. This alkyne we can use as a useful synthetic intermediate in the synthesis of cis or trans alkene. Okay, so this is this alkyne substrate can be used as a useful synthetic intermediate. So let us have this its forward synthesis. So in the end we have got this acetylene which is having this acidic proton. So let's treat it with sodium amide. So it requires the strong base, since this is the acidic proton, so it needs a strong base, sodium amide. So it will abstract the proton. Okay. In second step, this pentyl bromide. Okay, pentyl bromide will attack. Okay, so this is nothing but the SN2 reaction, substitution reaction. So we would get this. So this is alkyne. This alkyne derivative. This is our target molecule. Okay. So this is how we can make this alkyne derivative from the acetylene. So acetylene will react with sodium amide to give this acetylide. Okay, sodium acetylide. So this will attack at this carbon. So bromine will leave and it will form the bond, carbon-carbon bond. So it would end up with this alkyne derivative. So let's have another example. So before going to discuss these examples, so we would discuss the alkyne. Alkyne substrate is used as an important synthetic intermediate. Okay, why? Because this alkyne intermediate can be used in the synthesis of cis or trans alkene. So cis alkene can be prepared by using Lindlar catalyst, and trans alkene can be prepared by using Buss reduction of that alkyne substrate. Okay, so our target molecule is the alkene. So let us see this example. The target molecule which is having the trans double bonds. Okay, so we know the trans double bond can be prepared from alkyne by using the Buss reduction. So now we know the trans alkene can be obtained from the alkyne by using Birch reduction, and cis alkene can be prepared by using linear catalyst. So when you have this when you treat this alkyne with sodium in the presence of liquid ammonia, which gives transalkene. Okay, and when you treat with enlarged catalyst, it gives Synt, which gives G-alkene. Okay, so let us have an example where our target molecule is having E-alkene, so which can be obtained from alkyne. So let us see retro synthetic analysis. Okay, this is our target molecule. So here we have this E-alkene. So that means this E-alkene can be obtained by using Birch reduction of alkyne. So let us do this. First of all, we have this ester group, so we can include this bond. So it will have the negative charge, so it will acquire this proton, and this will have acid. Okay, this is acid, and this is alcohol. So now this substrate will treat as a target molecule. So let us put this arrow, and after FGR, this transalkene, this E-alkene, we can write like this. This E-alkene can be obtained from its corresponding alkyne. Okay. So this E-alkene can be obtained from its corresponding alkyne. So now we have this alkyne and this terminal methyl group. So let us cleave this bond, carbon-carbon disconnection. So we will have terminal alkyne plus methyl iodide. So here we can add proton. Okay. So now we have another carbon-carbon disconnection. So this, let us put another carbon-carbon disconnection. So we will have these will have bromide plus this acetylene. Okay, H and this. I have written here directly chemical equivalents. So rather than their synthons. So now we have this starting materials. These are our starting materials. So this is how we can do the retrosynthetic analysis for this particular target molecules. So when you look at this molecule, you will observe two functionalities. Okay. So one ester functional group and another is alkene. Okay, and that alkene is E-alkene. So that means this E-alkene can be obtained by using Birch reduction of alkyne. Okay, so since our molecule is having the ester group, so initially we can clear this CO bond, so that we would get this alcohol and acid. So in the next step, so we can transform this olefin to alkyne. Okay, since this olefin can be obtained, this particular E-olefin can be obtained by using Birch reduction of alkyne. So we can do HCl in this step. So we can convert this olefin to alkyne. So we would get this alkyne derivative. Then of course this terminal alkyl group can be generated by substitution reaction. Okay, with the help of strong base and alkyl halide, so we can generate this kind of alkyne derivative. So we have made this disconnection over here to get this alkyne derivative, derivative. So later on, as I said before, this terminal alkyl chain can be prepared by using substitution reaction. Okay, so we have this terminal, this long chain, so we can disconnect this bond, carbon-carbon bond, to get this starting materials. So here I have written directly chemical equivalents rather than their synthons. Okay, so this is all about the retrosynthetic analysis for this particular target molecule. So let's have its forward synthesis. So in the end we have got this bromo derivative and other end is having hydroxyl group. So before going to react with this acetylene molecule, so we need to protect it, otherwise it will create the problem. So we will protect with the help of this protecting group, that is tetrahydropyran in the presence of H plus. So we will get this okay. So we can this group okay tetrahydropyran. This is the tetrahydropyran. This can be used to protect the alcohol, okay, hydroxyl group. So we can write THP, okay. So then in the next step we will use this acetylene to get okay. So here, when you treat this bromide with acetylene, okay, in the presence of sodium amide, strong base, okay, when it treats this bromide is treats with acetylene in the presence of sodium amide, which gives rise to this acetylene. Then another treatment of sodium amide, then treatment with methyl iodide will give this okay. So we can add this methyl group over here by using this alkylation reaction. So then which reacts with sodium in liquid ammonia. This is the first reduction. So it gives protection with the help of this H plus, and in the second step we'll do this acetylation so that we'll get our target molecule. So this is how we can achieve the synthesis of our target molecules. So what we have done in this, we have started with this bromo-alcohol derivative. So since in this both the functional groups are reactive, so we need to protect this hydrogen group with the help of this THP protecting group. So it will, this hydrogen group can be protected with the aid of this acid catalyze this protection. Okay, so it gives this THP protecting group over here. So in the next step we have this halide, alkyl halide. So we can treat with acetylene in the presence of sodium amide. So this sodium amide will abstract this acidic proton of that acetylene, and that acetalide will attack at this carbon atom in Synt-II fashion. So it will give this terminal alkyne. Okay. So in the next step we will also use the sodium amide as a base. So it will abstract this proton. So again it will react with another molecule of other molecule of methyl iodide. So as to get this terminal methyl. Okay. So now in our substrate we have this acetylene. So we can convert this acetylene to transalkene with the help of Birch reductions. So Birch reductions. So when this alkyne treated with sodium in the presence of liquid ammonia, it gives rise to transalkene. Now we need to deprotect this THP group. So with the help of this acid catalyst, so we can deprotect. Okay. So as to get this 3-alcohol, and this 3-alcohol can be treated with this acetic anhydride to give this ester functionality over here. So in this way we can get our target molecule. Okay. So this is how we can apply this alkyne chemistry in this particular target molecules. Okay. In the next lecture we will see the more interesting problem which involves the carbon-carbon bond disconnections. Thank you.